going to go ahead and get started. Thank you all for coming to this in-person hybrid Zoom in-person tap colloquium. Our speaker today is going to be Dr. Juno, who's currently a National Science Foundation Sciences postdoc. He's currently working at the University of Iowa with great crowds. Before starting that postdoc, he completed his PhD under the supervision of Will Dorwin and Jason Tenbarge, who at the University of Maryland. Throughout his PhD and through his current postdoctoral position, he's been an active developer and collaborator with the Jekyll team at the Princeton Plasma Physics Laboratory. And he is leading the development of novel computational methods for the STEM of plasma physics. He'll be telling us about that today as he takes a deeper dive into this. All right, let him take that dive. If there are people in the room who have clarifying questions, please raise your hands and we'll attempt to here. For people that are on Zoom, if you could hold your questions to the end and then indicate that you have a question with the hand raised, and I'll do my best to actually mediate that conversation. Again, this is our first attempt at running this hybrid, so I appreciate your patience. With no further ado, Dr. Juno.
Thank you, everyone. This is all very new to me too, so hopefully it's as much fun for you as it is for me. As Chris said, I would very much like to take a deep dive into the distribution function. Specifically, a lot of my research, both in graduate school and through my postdoc, has been about how we leverage what I call phase space to understand weakly collisional systems. And I'm going to define a lot of this jargon very, very shortly. But before I do, I really do want to acknowledge everyone that Chris just mentioned, my mentors, as well as the entirety of the Jekyll team, which is the code, as Chris said, that I work on. And none of this research would be possible without them. So, weakly collisional, what does that mean? Well, as it turns out, if we look at all of the plasmas in the luminous universe that we can see, whether it's the heliosphere, the accretion disk, or the intracluster medium, all of these plasmas are weakly collisional. This collisional mean free path, lambda MFP, the characteristic scale on which particles travel before their dynamics are appreciably deflected by interparticle collisions, that scale is much, much larger than other length scales in the system, such as the plasma physical scales. These are the gyroradii, the scale by which particles rotate around the magnetic field, as well as what I denote the scales of the turbulence with this script L. Now, what is a practical consequence of this parameter regime where this collisional mean free path is so large? Well, you think about your favorite hydrodynamic models, things like magnetohydrodynamics. Formally, when we derive these models, we are deriving them in the limit that this collisional mean free path is small compared to the length scales that we care about. And so we can ask a question about what is a better way to think about these systems, to model these systems. Well, you might naturally ask, we're doing classical mechanics. So I know what the acceleration is. Why don't we just do F equals ma for all of these particles? I know how these particles should move, and I should be able to gain intuition from that. The thing is, this is a many-body system. And by virtue of having many bodies, this is not feasible. The second we're trying to understand how every single particle is being interacted with by every other particle in the system, we get very, very expensive computational algorithms. And it's not actually the case that that's necessarily very useful to take this deterministic perspective to track individual particles and understand what individual particles are doing. Instead, what we might consider is a perspective shift, one in which the collective effects, the particles all essentially moving together, matter more than these individual particle-particle interactions, one in which the sum is greater than the individual parts. And shift from this deterministic system where we're thinking about how individual particles are moving to a probabilistic one, where we're thinking about particles in infinitesimal volumes and what's the probability of finding them there. And that leads us to the fundamental object of interest to me and of interest to a lot of other astronomers, plasma physicists, you name it. The particle distribution function, scalar function f, as a function of x, v, and t, that encompasses the probability of finding particles in a given xyz or velocity position, just a small infinitesimal volume. This object evolves via the Boltzmann equation. So this evolution equation has advection in this high dimensional phase space up to 6 dimensions. And on the right-hand side here, this C operator is what is often called the collision operator. It's encompassing these discrete particle effects that we're smoothing over, we're coarse graining over in this perspective shift from a deterministic system to a probabilistic one. Now, for a plasma, the phase space flux alpha here, the characteristics for how the distribution function is advecting in phase space are very natural. We know that the particles' positions is affected by their velocity, and their velocities are affected by the Lorentz force. But there are other extensions to the Boltzmann equation, or other flavors. We could think about not having any forces. It's often called the free streaming element. And this equation system describes neutrinos streaming out from a supernova remnant and other systems like that. Or we could think about the force coming from some sort of potential. And then we would be looking at like a self-gravitating system or an electrostatic plasma. In all these cases, when we have these forces, we now need to close the system. We need to know how these forces evolve. For plasmas, it's very naturally Maxwell's equations. And these velocity moments, such as the current density, are given by velocity moments of the distribution function. So we now have a closed system coupling the Boltzmann equation to Maxwell's equations via these integrals of the distribution function. A couple of notes immediately about this equation system that is so fundamental. One, it's nonlinear. These electric and magnetic fields themselves depend on the distribution function via these velocity moments. And two, again, it's high dimensional. This distribution function is up to 6 dimensions plus time. And so that leads us to an immediate question about how do we deal with a fundamental equation that is both nonlinear and high dimensional. We know that we're going to need the computer. And it's very natural to think about things like Monte Carlo methods, where you would discretize this distribution function via essentially macro particles, these particles that are approximating many particles, advance them along characteristics, and then approximate the distribution function that way. But there's a problem with that approach, and that is the pollution of your solution with counting noise. Now, this counting noise is a real travesty because the particle distribution function is such a rich tapestry of the underlying physics of this system. Not only do you have the ability to essentially create spectacular movies of this evolution in phase space, there's actual real information in this phase space evolution that we should be able to leverage to actually understand this system. Not to mention the fact that as our measurements have gotten better, we're also just consistently getting higher quality distribution function data from a variety of spacecraft missions, such as the magnetospheric multiscale mission, which crossed a reconnection site and was observing electron distribution functions with these interesting crescent shapes that seem to be indicating actual physics of the reconnection site. I'm talking very abstractly about what is actually contained in the distribution function. So it's worth actually taking a simplified textbook example to really illustrate this point about actually leveraging the distribution function to gain some insight into plasma systems or other weakly collisional systems. So to do that, I'm going to do what's called a Landau damping of a wave, specifically a Langmuir wave. But the essential idea is that I start with this electric field perturbation in a plasma and I let it evolve. What's going to happen is actually this electric field is going to lose energy. It's going to energize the particles. And it does that through this process called Landau damping, which has an exact analogy with surfers on a wave. Essentially, what's happening is particles that are moving slower than the wave, slightly slower around that phase velocity, they can gain energy from the wave, while particles that are moving faster will lose energy. But this is an energization process because there are more particles moving slower than the wave than faster. And so in analogy with the surfer gaining energy, you take energy from that electric field and energize the plasma. And you can immediately look at this f of x and think, Well, the distribution function probably is deformed around that resonance. Indeed, it is. Now, I'm going to talk at length later about particular diagnostics, but what I want to illustrate with this diagnostic called C sub E is that we can actually diagnose around the phase velocity of this perturbation evolving, essentially a motion here. So this blue is actually corresponding to blue-red signature is actually corresponding to motion of energy. Particles are being energized. More on this in a moment, but just to conclude that this point about the distribution function being this fundamental object that really does provide insights. Now, how should we proceed? Given the fact that we really would like to leverage the distribution function to understand these systems, what should we do? So we can look at our equation system and we can ask what it would mean to directly discretize this equation on a phase space grid, to derive and implement a 6-dimensional partial differential equation solver. Now, we've done this as part of the Jekyll simulation framework. And yes, if you're curious, amongst the development group, there is a more unstable branch called Hyde that is not for public release because it behaves poorly. But Jekyll is a general purpose open source framework that has a variety of equation systems in it. And I'll be focusing on the solver that works on this equation. For your general interest, there's 2 pieces to it. But if you're curious about language and documentation and GitHub links, these slides will be publicly available, and I encourage you to check it out. I also have had the pleasure to work with a number of people on a lot of these algorithmic developments that I would love to tell you more about, but I think it would be worth actually moving on to justify all of the sweat and tears, and if we're honest, a little bit of blood that goes into code development. So let me just leave this further reading for you for now in terms of the overall algorithmic developments that went into this whole package. With one caveat, I really do want to emphasize of what it means to do a grid-based method here, because you may have intuition of things like finite difference and finite volume methods. And I really want you to think about what it means to discretize this high-dimensional equation in this way, specifically with what I call the discontinuous Galerkin finite element method, which you can think about as a natural generalization of a finite volume method, one in which you're discretizing your domain into cells, some triangulation or tessellation, and you're evolving a single piece of information in each cell, but there's no reason to restrict yourself. You could think about evolving 2 pieces of information, a cell average and a cell slope, and thus have a piecewise linear representation within each cell, or go further. Essentially, I'm going to have a representation of the distribution function in individual grid cells in up to 6 dimensions. Now, let's do some science. We know the universe is magnetized. And so if you just think about a galaxy cluster, in this case, Abell 2199, you can see just from the X-ray emissions, basically constraints on how much of that mass is thermal plasma, what its temperature is, what its density is, etc. Turns out, when we take magnetic field measurements, we find something surprising. See, we would say that a system is magnetized if the gyro radius was small compared to some other length scale in the system. The gradient length scale is on the order of 100 kiloparsecs, pretty big, and you could have a kiloparsec size gyro radius, and that would be small, right? That would lead to a magnetized system because the gyro radius would be much smaller than this gradient length scale that you think is driving other dynamics in the system. The thing is, the magnetic field's much smaller than that, or much larger than that, excuse me. The magnetic field is actually on the order of a microgauss, 12 orders of magnitude larger. Why? Well, we have a lot of theories for this. And the most compelling one is something called the turbulent dynamo. The thing is, the dynamo, this action by which the magnetic field is stretched and compressed and grown via the turbulence, requires you to start with a particular magnetic field. It actually requires you to start with around this size of a magnetic field. So, okay, dynamo will get us from here to here, but how did we start here? How did we have that initial seed magnetic field that allowed us the turbulent dynamo to take over and then eventually lead to this magnetized system? There's a lot of debate about this. And in fact, it's probably a fairly subtle question in that there's different processes that proceed in a hierarchical fashion until the dynamo takes over. But one particular seed field candidate I want to talk about that could potentially get you at least here, something called the filamentation instability. Now, the filamentation instability is a fun little plasma instability in that it just naturally arises from streaming plasmas. When I have particles basically moving to the left and right in some Cartesian box or just general some domain. You might get these from shocks colliding, from large-scale shear flows, you name it. It's a very standard thing that can happen in many systems, just particles streaming through each other or moving back and forth. The thing is, if you had some infinitesimally small magnetic field perturbation here, then what would happen is the streaming particles would deflect slightly, which would actually drive a current. And then this current would then support the magnetic field and grow. And to the point that even if you started with some asymptotically small magnetic field perturbation, you would grow that magnetic field perturbation via this deflection of these streaming particles and the growth of this current. But this is just 1D, and the universe is not 1D. So we can ask, what does this parameter space look like? And we're going to look at this parameter space as a function of two variables. This drift velocity over the speed of light, basically how fast the particles are moving through each other, and their thermal spread with respect to that drift velocity. Basically a proxy for how much energy in that plasma is initially internal versus kinetic. Now what I'm plotting here is theta, the angle of the fastest growing mode. And I'm defining 0 degrees as this filamentation instability and 90 degrees as the two-stream instability, which was something you were seeing earlier with that phase space evolution. Now, in higher dimensions, these instabilities can compete with each other, in addition to the fact that there are hybrid versions of these modes. While on the relativistic side of things, when these flows are very fast, the filamentation instability is robustly the fastest growing mode. It's always going to grow extremely fast and dominate the dynamics, such as in a laser plasma system or a gamma ray burst. Remember, we're actually concerned with a different setup, one closer to the earlier universe, maybe around the reionization epoch, where we're asking the question of how did we get that seed magnetic field for the turbulent dynamo to take over? And so where we are is more along this vertical line with these red X's here. And we can consider basically just different variations in this thermal velocity to drift velocity ratio. We can consider something where the two are comparable in size, and we get basically these dispersion relations, where the important thing to note with respect to the fastest growing mode in K is that it is robustly the two-stream instability, it's 90-degree mode. But as we move colder, as we reduce the amount of energy that is initially internal versus kinetic, in fact, there are many modes that all have comparable growth rates, just linearly. So what's going to happen in nonlinear simulations? Well, that's what we were kind of interested in exploring. So just to give you a sense of the geometry and the initial condition, we're going to do two spatial, two velocity dimension simulations. We're going to start with initially Maxwellian plasma. This is drifting, streaming through each other, particles moving basically to the left and right. And we're going to start with a very, very, very small magnetic field and electric field perturbation to try and ask the question, how could we even get to the small magnetic fields that are needed for the turbulent dynamo? Yes.
Quick basic question. You say streaming through each other and then you compared it to shear. But
Yeah.
Streaming through sounds like two different types of particles interwoven versus shear is something very different. So I guess I'm a little confused about what the trigger is there.
So even in shear flows, right, like there, you could have, yes. So I completely understand the question. Right now, this setup is like the two populations are already like streaming through each other. They're already superimposed. This exact same instability shows up in a shear flow where there is like one population that is moving one direction, another population moving a different direction that are sort of displaced in space.
Two separate fluid components. It's not happening, right?
two separate fluid.
Does this require two different fluids or one fluid?
Remember that I'm thinking about like in this case, in a kinetic system where I have a distribution function, I don't need necessarily two different fluid components. It's all the same system. And then I can have like one population moving in one direction.
Right, so but the physical setup, are you imagining relative motion of ions and electrons? Or
Right now, yeah, I'm doing relative motion of two electron populations.
electron population?
Yes. Thank you for the clarifying question. Important to note that I am just talking about electrons here for the moment. And this is their initial energy densities. Now, I want to show the nonlinear evolution of this quote unquote hot case, where the initial thermal velocity is comparable to the drift speed, 0.5. And what you'll see here in this movie is the evolution of a couple of different things. You see the evolution of this EY electric field, the BZ magnetic field, which will be intrinsically linked throughout the simulation. You'll also see the evolution of cuts of the distribution function, one that's showing the distribution function Vy as a function of y. So here's our two populations that are streaming through each other, already superimposed in space, moving up, essentially up and down the domain. And then a cut at a particular spatial location, x and y, showing their velocity distribution functions as a function of Vx and Vy. On the left here are the electric field energy and the magnetic field energy as a function of time. And you'll see a red dot appear that basically is tracing this evolution as a function of time. Now, in this hot case, recall that the two-stream instability is the fastest growing mode. And so, in fact, this initial evolution here actually is quasi-one-dimensional. You're essentially only getting structure in Y, until actually that structure breaks up. And what you're left with is a growing magnetic field. What's going on here? Well, this is actually a secondary instability that is cropping up later in time in the simulation. Basically, because of the initial growth of the two-stream instability that was quasi-one-dimensional, my final distribution function is actually hotter in Vy than Vx. I have a temperature anisotropy at the end of the simulation. And that temperature anisotropy supports the Weibull instability, a cousin of the filamentation instability. That then leads to this saturated magnetic field state. Basically, by the end of the simulation, about 1% of the initial kinetic energy is in the magnetic field. We have actually gained a magnetic field as a result of this instability. But the situation is really quite different as we reduce this, this ratio, as we make the internal energy much smaller than the initial kinetic energy. What happens now is as the system evolves, we develop a lot more structure in the electric and magnetic fields. And we even develop more structure in phase space as well, as the whole system winds and twists up as a result of not just one mode, not just the two-stream instability, but these oblique modes, these mixtures of the filamentation and two-stream instability. And the resulting distribution function at the end is actually much more isotropic. There's really no difference in the temperatures between these two degrees of freedom. As a result, the magnetic field collapses. There's actually no real magnetization at the end of the simulation. We can be a bit more quantitative with this and talk about this energy exchange, because in the hot case, when only the two-stream instability was really dominating, we ended up with a temperature anisotropy, another source of free energy, something far from thermal equilibrium. Whereas in the colder case, this distribution function ended up much more isotropic, and in fact corresponds to basically the plasma giving all this energy to electromagnetic fluctuations and then getting it all back as internal energy. And so we mapped out this parameter space. This is again the magnetic energy and the electric field energy as a function of time for a number of different test cases, ranging from blue, the coldest case, to red, the hottest case. And what we found was that we were really seeing a noticeable transition around when the thermal velocity over the drift speed was about 1/5, that only was showing up when you went to this higher dimensional case, when you were introducing this additional physics from this instability competition. Because if you just did 1D simulations, shown here in dashed lines, you're always getting magnetic field growth. The filamentation instability is always efficient at generating a magnetic field that can ultimately assist in the overall magnetization of the universe. It's only when you introduce the higher dimensional physics, when you introduce the instability competition, that you see this magnetic field collapse. It's worth asking, why was Jekyll one of the first actual simulations of this? Why were there other simulations in similar parameter regimes that were not seeing this magnetic field collapse? So what we did was we decided to compare it to this traditional Monte Carlo method, this method that is very popular in the community that generates this particle-based discretization of your underlying equation system. Turns out, you get something kind of interesting, which is that depending on the number of particles per cell you run with, you're getting these pseudo-saturated magnetic field. So this is still the magnetic energy as a function of time. And then I'm varying this NPPC, which is essentially the number of particles per cell. Basically, my actual phase space resolution within my particle-based method. And it is only as we move to very high particles per cell that we start to match this Jekyll result in purple. What's happening? Well, as it turns out, our distribution functions are quite noisy as we have lower particle per cell resolution. Essentially, as the system evolves, we're filling phase space, and our effective phase space resolution is decreasing as the instability grows. Ultimately, this is perhaps unsurprising. We've always known in numerical methods that some problems require more resolution. But it's important to keep this in mind when we think about some of these sensitive instability dynamics for the actual plasma systems we're interested in. Because when we have these cases in which the dynamics are actually sensitive to this resolution, we really do want these complementary tools that allow us to actually diagnose this physics. In the second half of my talk, I actually want to transition to a different topic, which is basically what happens when the Monte Carlo method is just as good? Because this method has existed for a long time. There are lots and lots of particle and cell simulations doing a wide variety of plasma systems and studying exactly what this kinetic system is doing. We're not saying when we come in with our continuum method that everything that's ever been done is wrong. We are a complementary approach. But can we still provide insights when there is a long history of success with this numerical method? I like to argue yes. And I want to do that with a collisionless shock. Now, by collisionless shock, I mean the types of shock waves that we'll observe throughout the universe, where because, again, we're in this weakly collisional system, we're in an interesting parameter regime when it comes to a shock wave. Take the Earth's bow shock, for example. When you consider the supersonic solar wind flowing in, encountering an obstacle, in this case, the Earth's magnetic field, what we observe is that the bow shock's length is much, much smaller than the collisional mean free path. So our intuition for how this supersonic solar wind must stagnate and shock around this obstacle is different than the same intuition we might have for a bow shock here on Earth for like supersonic airflow around a fighter jet, for example. So there must be collisionless processes that are actually leading to this flow stagnation, eventually leading to the energy conversion from this large amount of incoming kinetic energy to other forms of energy, such as electromagnetic and internal. Now, this is a really well-diagnosed system. We've got a lot of really interesting measurements throughout the entire time we've been sending spacecraft into the near-Earth environment. Just to take the magnetospheric multiscale mission as an example, again, it's not just that we have the temperature through this bow shock. It's not just that we can clearly see as we cross the bow shock, the temperature increased. We have the corresponding distribution functions associated with that temperature increase. So if we understood this distribution function structure, we would understand exactly what collisionless processes are at play in terms of why is the temperature increasing. Now, how should we understand this? Well, what I want to do is I want to look at the Boltzmann equation here. I want to ask what terms are actually responsible for energization. The energy is defined as the 1/2 mv squared moment of the distribution function. When you take this 1/2 mv squared moment of your whole Boltzmann equation, you get an evolution equation for the energy density, which has a number of familiar terms, things like the energy flux, and the heat flux. Excuse me, but these terms just correspond to movement of energy. What I want to know is how the plasma and the electric field are exchanging energy. And so what I want to do is I want to take a step back from this velocity moment. I don't want to just consider bulk energization. I don't want to just consider how the fluid part is being energized. I want to look at velocity space. And I do that with the C sub E diagnostic I referenced earlier, where now I actually do want to look at how this energy is being exchanged in phase space, looking at essentially correlating this electric field with these gradients of the distribution function. This is exactly what I was showing earlier, where I was thinking about Landau damping of these waves and trying to understand, well, if the waves are damping, if the waves are giving energy around the phase velocity, then that gradient should correspond to where particles are being energized. Right around the phase velocity, there'll be this blue loss moving to this red gain, where the particles are essentially moving from lower to higher velocity, moving to higher energy. And this is a well-established diagnostic. It's been around for a number of years, and you might have heard people here at Arizona talk about it because the pioneers are here at Arizona. So the particular shock that I want to look at initially, just as this proof of principle, is a very simplified setup called a perpendicular collisionless shock. By perpendicular, what I mean is that the magnetic field is actually going to be completely perpendicular to the shock normal. So this is just some parameters for your reference in the Vlasov simulation. So, oops, sorry. Nope. It's a reduced mass ratio, beta order 1, non-relativistic, fairly small simulation, but just to try to get an idea of how we can characterize distribution function structure in shocks. And so this is kind of what the fiducial simulation looks like, where there's an initial transient period before this compression of the magnetic field starts propagating. This is my shock wave. And we can see corresponding structure through this compression of the magnetic field in our distribution functions. We can see here in the electrons, there is some broadening of the electron distribution function in Vx, function of x. Likewise, there's this interesting reflected population of the protons. So what's going on here? Well, what I want to argue is that this phase-space structure really does tell us a story about what's going on in the system, and we can actually diagnose this. See, if we look at basically the distribution functions through part of the shock. So I'm defining the upstream of the shock is here, downstream is here. I really want to focus on just this region here. Ions and electrons here. So here are the ions, here are the electrons. See, I want to actually hone in on this population of the ions and the broadening of the electrons. Specifically, what is actually leading to this high energy tail? And how can we characterize this distribution function structure? So this is where our field particle correlation diagnostic is really going to help us. And we're actually going to be able to leverage this pristine noise-free distribution function to characterize this information. So here is again the proton distribution function as a function of Vx and Vy. Here's that same reflected population. And here's basically the fields with some normalization. So you have a good idea of exactly how the fields are varying. Because in the shock rest frame, the Y electric field should be relatively constant. And then you have some compression of the Z magnetic field. What I want to do is a small frame transformation to make this especially clear. I'm actually going to calculate the field particle correlation in the shock rest frame. So I'm going to transform the y electric field by a Lorentz transformation, and then the distribution function as a function of Vx will also be shifted. Now get this, what's going on here? So similar to the Landau damping picture, there seems to be an actual motion in phase space of energy. Particles moving from this blue region to this red region, higher velocity, higher energy. We can't actually gain intuition in what's going on here with a single particle motion. This is a well-studied energization mechanism called shock drift acceleration. Essentially, when particles encounter a magnetic field gradient, they can be turned around and move back upstream, where the magnetic field was less in magnitude. And when they're back upstream, their Larmor motion or their Larmor orbit should be larger. They'll spend more time in this lower magnetic field and thus be able to gain energy along that electric field, which is supporting their incoming motion, supporting E cross B. Ooh. To be more clarifying about this actual single particle motion, or this shock drift acceleration energization mechanism. When we have these particles moving through this region of smaller magnetic field, they cross this gradient. They move into a region of larger magnetic field, an exact analogy with what's happening here in our actual simulation. They can, because their Larmor motion is smaller, depending on their gyrophase when they enter this, they will in fact be turned around and then can move back into this region of smaller magnetic field. When they do that, you will then be back in a region where your Larmor orbit should be bigger, and thus you'll spend, quote unquote, more time in this region. But there is a Y electric field there, and thus you can gain energy. Turns out if you map this same single particle motion into where you are in velocity space, you see that this red part of the trajectory, where the particle is back upstream, is exactly where the particles are gaining energy. So what we have here in our simulation is a phase space energization signature for this classically understood energization mechanism. A mechanism that was previously understood in the context of particle motion, now understood in the context of phase space. Okay, but yes.
You just kind of described what we knew about long ago confirming and cosmic ray acceleration.
What I am trying to do is argue that in this case, there are useful things to be gained from the distribution function. Now, in this particular plot, yes, all I have basically found in phase space is a well-understood energization mechanism going back decades. That is known from just watching particles evolve. If those particles move into a magnetic field gradient, they can undergo this energization process. But your question is pertinent because it leads naturally to what actually is the use of these distribution functions. Because as related to the previous clarifying question in the talk, I have the whole distribution. I have all of the different populations of the plasma. And so with all of phase space, I could actually try to understand how different populations are being affected energetically. To do that, I actually now want to look at just this X electric field. So I'm looking here, and then at this point B, and I get this field particle correlation signature, which is a bit more complex in terms of its overall structure. It turns out that actually we have multiple distinct populations within this particular signature that correspond to how these different populations of the plasma are being affected by the electric field. Of course, the incoming beam is being stagnated, is being slowed down by that particular electric field. But in fact, there are other particles that are actually being accelerated back upstream. And so unlike in the Lagrangian sense, or when you're just tracking single particles, where you do have to think about like, oh, how does every individual particle be affected by the electromagnetic fields? Now you can take this whole picture of phase space and try to understand how these different populations are being affected. In fact, I want to generalize this to go beyond this perpendicular shock, where we were just considering a system that really only had this Z magnetic field undergoing compression, and move into a situation that is more realistic. In this case, in oblique shock, where now the shock normal angle is inclined with respect to the incoming shock. And in fact, there'll not only be an initial Bx, then the Bz will undergo compression. And so in this case, with all of my electromagnetic fields, Ex, Ey, Ez, Bx, By, Bz, almost all of them are dynamically important now, as is the case in a real shock. And in a real shock, you'll get more complex particle dynamics that we hopefully can understand in the distribution function. So now we have this additional plane of the simulation. And if we try and squint, we might be able to tell that something is actually going on in this Vx, Vz plane. It's a little bit easier if we plot log of the distribution function. Because now, not only do we have this same picture as before, there is this reflected population in Vx and Vy from encountering the magnetic field gradient. Now it seems like there are distinct populations in this Vx, Vz plane. And if we look at the field particle correlation in that plane, we're getting distinct signatures as a result corresponding to these two distinct populations. Let's look at our movie again and look at some of these particles, trying to distinguish exactly what different protons are doing. Many of them are now upstream, they're gaining energy, and they're about to hit the magnetic field gradient again. Some of them, when they hit that magnetic field gradient, such as these ones down here, well, they just move downstream. They've hit the gradient once, and they've been energized once, and now they're downstream. Some of them were reflected multiple times and underwent this process multiple times. And so if we think about what this should look like in phase space, it is actually easiest to look at in this Vx, Vz plane. As the particle comes in, it's reflected once, reflected again, and we should see this stair-stepping pattern that corresponds to this multiple bounce energization that actually is reasonably clear as a result of this continuum kinetic simulation, that we're able to actually pick out the different populations of the plasma that are being energized still by this same process. So one can ask, despite the difficulties in doing this type of analysis, can we do it with our standard methods, our standard well-tested methods that have worked for decades to do these same types of shock simulations? And I actually am now going to employ a slightly different method. I had both the ion and electron dynamics throughout this talk, but I just want to look at the ion dynamics just for the purposes of this illustration. So I'm going to do a hybrid particle and cell code. Basically what that means is that I still have the Boltzmann equation for the ions, but now the electrons are a set of simplifying assumptions where, because the electrons are assumed to be asymptotically lighter than the ions, I can ignore their inertia, and I will just take a particular equation of state, in this case an adiabatic equation of state for the electron temperature evolution. Now, what I actually want to do to really illustrate the complexities here is I'm going to do the most general 3D hybrid simulation. I'm still going to really focus on just the shock dynamics, but I am actually going to do a 3D 3D simulation with many, many particles per cell at what's called reference density 1, and even a higher velocity, so that I'm actually doing what I would think would be an easier problem on this front, because there's going to be more energy to energize these particles. There's a larger amount of kinetic energy in that reservoir, so that more particles will be energized. It's a similar geometry in that the X domain is still where I'm injecting plasma, so that there is a shock that will propagate through the domain, but my other two dimensions, Y and Z, will be periodic. Now, taking a 1D cut just at Y equals 0, Z equals 0, and looking at the 6 electromagnetic fields, EX, EY, EZ, BX, BY, BZ. It is a similar case as before in that BZ is our proxy for where the shock is, because that's where the compression of the magnetic field is. But you can see, because we're in 3D and we're just taking a cut, there's structure in all the electromagnetic fields, including BX this time, since I'm not doing a 1D simulation. Now, to get actual statistics on the distribution function, to be able to calculate these gradients and determine what the actual energization is, I need to do some averaging. So I'm going to average over a small domain. Half a DI is characteristic scale in the plasma, in X, and 3 DI in Y and Z, with a particular velocity bin of half of the Alfvén speed. So I plot the distribution function. Looks like we can clearly see that reflected population. Maybe something's going on here. Again, a little bit easier to see in log space, where I take the log of the distribution function. This looks exactly like before from my Jekyll simulation. Looks like this beautiful reflected population. But when I try and pick out what I think should be happening with these multiple reflected particles, I'm having some difficulties. And it's clear, even in the field particle correlation, that while this beautiful shock drift acceleration signature is the same between my continuum and particle-based method, I'm having some difficulty with the actual, what I think should be here for these multiple bounces. Let me work harder. Let me do more averaging. And now I am seeing a little bit more of that population that I expect to be there. So there should be this gap in velocity space. Here's the first bounce. Here's the second bounce. Let me work even harder. Let me do an even larger particle per cell count simulation. It's sort of there, but it's really not showing up actually in the field particle correlation. And there's a number of reasons for this. One, the noise inherent to the system, and two, to actually get my particle statistics, I'm averaging a lot. I'm smoothing over my representation of these gradients. And so when I compare my actual hybrid results to my Jekyll results, yes, there is more physics in this hybrid result. It's full 3D, 3V. There are even instabilities present, but I just want to look at the shock energization. I just want to leverage the distribution function to say a little bit more about what's going on. And really, it's hard with PIC codes. So I do want to argue that these continuum methods really do provide a complementary approach to this. If I had to summarize my talk and just, well, actually, first, let me talk about real data first. I mean, this is not just theoretical. We have these types of distribution functions when it comes to what we see in the data. So the thing I want to focus on are basically these distribution function plots in what is the same Vx, Vy plane as what you were seeing previously. And you'll see these dashed lines in the MMS data that are basically encapsulating a zoom in of all of these distribution functions. So this is basically time. So we've got 15 instances in time that all span these two dashed lines. And as the spacecraft flies through the shock, we can see the evolution of this distribution function. And this is what we want to characterize. This is what the principal motivation is for actually doing all of this work. That when we have access to the distribution function, we are able to make these kinds of comparisons to observations potentially more easily. So really, if I had to summarize the talk in just 2 points, it's that continuum kinetic methods are really this nice complementary tool. Sometimes it just makes the analysis easy. Sometimes in the case of these shock simulations, while some of these things are known, by having access to the distribution function, you can really characterize how different populations are being energized. But then there's the bigger potentially useful thing, which is in that the elimination of noise really does permit us to eliminate a source of error, which may be polluting our physics. Which kind of leads me to a frontier that I think is potentially of interest to the larger community. We just recently got a grant funded to do some relativistic astrophysics work. Specifically, we're looking at compact objects. And one of the first things that some of our collaborators were asking us about is whether or not we can help on this problem of coherent radio emission from pulsars. So it's been known that this radio emission from pulsars is kind of puzzling. How do you get the actual bright coherent signal that's observed? If we know it has to be coherent, because if it was incoherent, the black body spectrum would say that the pulsars are way too hot. But if it's coherent, that means it has to be some plasma physical phenomenon, that the particles are actually doing these collective motions and leading to this radio emission. So there were a couple of theories for how this should proceed. Historically, things like instabilities and curvature radiation have been invoked. The plasma instabilities are completely unsatisfying. They just don't have the right growth rates to explain the timing on the radio emission. And curvature radiation sometimes works, but not always. There's been some recent work that suggests that basically just non-stationary plasma discharges, the sheer fact that the pair production should itself be non-stationary as the plasma works to screen out the electric field that the general relativity vacuum solution tells us should be there, will actually produce this coherent radiation. The problem is these simulations are very challenging to do for particle codes. There's exponential variation in density. You're going for a very tiny signal, some small amount of electromagnetic radiation from these particle dynamics. And from our perspective, there's a real opportunity here. These systems are so strongly magnetized, there are actually integrable degrees of freedom. And so if we could come in with our own perspective on how to do continuum simulations, instead of doing these full Vlasov simulations, instead do what's often called drift kinetics, but in the relativistic limit, where now we've gone from a distribution function that's 60 to one that's really only 40, because all that's really entering into the dynamics is the parallel motion, the motion parallel to the magnetic field. And in fact, the perpendicular motion is basically just the E cross B velocity. Then this may actually really provide a complementary way to study these systems. Because in an exact analogy to the history of fusion energy sciences, where there were a lot of particle-based codes for doing these highly magnetized systems that were really struggling in terms of signal to noise ratio, continuum methods could provide a natural way to assist in understanding these systems. Thank you for your attention, and apologies for the initial technical difficulties. I'd be happy to take your questions now.
Start off with the questions in the room. If not, we can also take any questions from Zoom.
General, those 2D simulations, right? And that's the energized, they're clearly separated. I was curious, could you blur those separations for changing, you know, your initial conditions to have like, I don't know, greater distribution of initial velocities or something? Or is it pretty much always going to be that clean cut separated?
Right, so the question was whether or not in the shock simulations, these different energized populations are really always as separated in velocity space, as clean as the particular example that I was showing. No. I think the answer to that is simply no. It is, there are parameter dependencies here. You can have these broad spectra of energized populations. It need not be the case that the populations are as cleanly separated as they were in the example. But I think that actually leads to the natural strength of the method, in that, as we were seeing in the particle-based case, because I had to do a large amount of averaging, I really was smoothing over what would have been sharper gradients. Now, in many cases, these gradients are not necessarily very sharp. This is basically a phase space resolution question. In cases where these gradients are not very sharp, yeah, I mean, a lot of the particle-based methods will very much succeed. And the ability to resolve these sharp gradients for these particular parameters is a real strength of the method.
Other questions?
So I'm trying to And that picture that you showed of shock drift acceleration, that movie, that nice movie that you had.
Oh,
Yeah, so I'm speaking to the interpretation of these, the separate population that you see in the shocks. So in this movie, you get the impression that the particles have pretty big gyro radius as they're coming in.
yeah.
But in your calculation, the thermal particles are essentially advecting with mostly advective motion. So they
Yes.
don't have that big gyro radius. They have a little wiggle on a line. And then I'm just wondering how some get selected to have this big gyro radius to come back upstream. You see what I mean? What's the
yeah.
selection process here?
So
Most of them would just seem to kind of go through and not have this big gyro radius and do what you're saying.
So the question is basically the difference between the movie here, which definitely more strongly emphasized the multiple bounces. You could see that actually some particles started with fairly large gyro radii at the start of the movie, compared to some of the earlier examples where, because the particles were thermal coming in, they were basically just advecting with the shock velocity and their gyro radii was small compared to that motion. The answer to your question is this movie is mostly generated to really highlight the example. And in fact, if I look at, for example, this particular Jekyll slice, it is the case that every particle here is coming from the thermal population. I didn't seed any higher energy particles in my Jekyll simulation. This population is smaller. There are fewer particles that bounce multiple times because I started with a thermal population and I didn't have necessarily very high energy particles to get reflected multiple times. So in many systems where the particles are higher energy, when they encounter these magnetic field gradients, they are able to bounce very effectively multiple times. There's even, my understanding is, there's even long debates in the community on things like shock surfing acceleration, where the particle would essentially skip along the magnetic field gradient and get to very, very high energies, but only if it was sufficiently energetic before it hit the gradient. Does that answer your question,
Well,
that I was
let me
distinguishing
let me
between?
hone it in. You're heading in the right direction. So okay, so you've run this calculation with your Jekyll code and you get these particles. So they come out of your code.
Yes,
Where did they come from in the initial phase space distribution?
all from the thermal population.
But where in that thermal population?
Oh!
From the wings of the distribution?
From the wings, yes.
Okay.
Yes, it is the case that the reason that this population is smaller is because it came from the deep tail of the thermal distribution. Only very
Okay, so
Yeah.
is it true then that the number that you get will depend on the relative weight between the advection velocity and the thermal velocity? Because that'll determine kind of how many particles you have out in the wings, right?
If I understand your question, the answer is yes. And I believe that actually is, again, a strength of this particular approach, because my representation of the deep tail in my continuum method is better than in my particle-based simulation. Even though I was running with tens of thousands of particles per cell, I didn't have many particles in the deep tail, even though they should have been able to reflect multiple times if they were there.
Yeah, thank you.
So we have two questions over Zoom. One of them comes from can people on Zoom speak through, or should I read through for them? Anybody else? I will read. Thank you for the very interesting talk. I have a question regarding computational cost. In particular, how does the Jekyll computational cost compare with the code computational cost when the two solutions from the two agree in that problem where a large number of particles per cell were necessary? is particle cell still computationally cheaper?
Excellent question. Let me bring back here. So I believe the question is referring to this comparison here, where the continuum kinetic method, it took many particles per cell to get closer to the continuum kinetic method. The answer is the Jekyll simulation for these particular parameters was about the cost of the green line here, the 1200 particles per cell, which you can clearly see is displaying the right trend, even if quantitatively there was a larger magnetic field collapse in the Jekyll simulation. As an addendum to that question, I would say that while there is a similar computational cost for this given physics, there are other instances where I think Jekyll will outperform Pick, and then Pick will outperform Jekyll. For example, in laser plasma problems where the signal is as large as it is, where you're hitting a plasma with a petawatt laser, and historically these simulations can be run with 10 particles per cell, that will be challenging for Jekyll to compete with. On the flip side of that, though, is, for example, the application I was talking about at the end. If you ask the fusion energy sciences community, what is cheaper, continuum drift kinetics or the guiding center Pick equations that are evolved for fusion, all of them, or basically all of them, will say continuum drift kinetics is cheaper. Because for the equivalent resolution, you are much more easily able to resolve these sensitive signals in this high magnetization limit, where it can be very, very difficult in a standard particle-based method to extract the physics you're interested in because the magnetic field is so strong.
Amar, you have your hand raised.
Yeah. Can I?
Set up so you can speak through.
All right. Can you hear me? Can you hear me?
Sound is.
Can you hear me or not hear me?
Unfortunately, Amar, the sound seems to not be coming through. I apologize.
All right. Okay, that's okay.
It was working earlier, I promise. Yep. Here we go. Amar.
Yeah.
Can you
So is that
comment
better?
on the noise in the Pick and how the averaging will modify the distribution, wiping out the structure you see in Jekyll?
Can you repeat the question?
Certainly. Can you comment on noise in Pick and how averaging modified VOF, wiping out the structure you see in Jekyll?
Right. So in the final case where I was trying to get as good of statistics as possible from the particle-based code and quantify these same gradients, one of the things that happens is when you're averaging over as large of a volume as I was in the attempt to get good statistics, I'm averaging over what is not necessarily a planar shock, and will be the case in other systems, for example, in turbulence, where there may be complicated reconnecting current sheets or other spatially dependent dynamics. So when you do as much averaging as I was doing in the hopes of representing these gradients, in the hopes of really leveraging the distribution function to understand this structure, it makes it just as difficult in some sense, because then you start including different plasma in the process of constructing the distribution function. I think a good example will be, if I can skip back ahead to the actual dehybrider fiducial plot. So when people do these 3D PIC simulations, you can see these fluctuations along the shock. This is often called shock ripple, and is the result of these instabilities that are present in the other directions, and is observed in the near Earth environment as well. We characterize this shock ripple. If I have to average over the entire shock ripple to try to get good statistics and try to characterize these gradients that can be helpful in understanding the physics, all of a sudden in one part of the domain, I may be further upstream, in another part, I may be further downstream. And that actually leads to an overall broadening of the features. So even in my attempt to get better statistics to more accurately resolve these gradients, I've made it harder for myself because of the different physics throughout the spatial domain.
Thank you. Any other questions? If not, let's thank the speaker again. For those here at Arizona, Dr. Juno is going to be here for another day, so reach out if you'd like to come and talk to him about any of these exciting results that he's talked about. Thank you, and hope to see you at future Colloquium over the next